Hi everyone, welcome to this fourth lesson in the Forces in Space scheme, and this is where our work on forces really begins. And it's an interesting lesson. It's another of the historical case study lessons that I think are really important for introducing core concepts. And the concept that I want to build in students, the way I want to get students thinking about the physical world throughout this scheme of work, is really the idea of Newton's first and second law, ideas about motion. And these are incredibly powerful and incredibly counterintuitive. And the purpose of this whole sequence of lessons, it's kind of 9, 10 or more lessons that comes after this, is to really help students understand why what we talk about this lesson is so important. So it's one of those lessons that looks kind of difficult to teach, and it's tempting to kind of skate over it, but it's really profoundly important because it sets up the kind of old way of thinking, the intuitive way of thinking about the world that isn't as powerful as this new way of thinking about it, which can unlock all sorts of understanding of various phenomena. So in the slides, what this lesson begins with is a basketballer shooting a three-pointer. And what I want to do in this lesson is get students to understand two ways of thinking about what's going on here. So we always seem to be setting ourselves up against poor old Aristotle, who was a very clever guy, but the scientific revolution did overturn a lot of the ideas he had around nature. It wasn't really his fault, in fairness, that they became dogma, his ideas, but anyway, we'll leave that for another day. But Aristotle had this picture that if you have the basketballer shooting the basketball, let's put the basketball up towards the basket, like this. Let's put the basket here, and I'll show the kind of arc of the basketball like this. So Aristotle's idea was that any object that's moving needs a force to keep it moving. So under the Aristotelian picture of the world, there must be a force that's pushing this basketball in the direction of motion. And this is how a lot of students will think, because if they're riding their bike along a flat road, let's say, they will have to keep pedaling, they'll have to keep providing a force through their pedals in order to keep moving. If they stop moving, if they stop pedaling, then they'll slow down and stop. So this is a really intuitive picture of what's going on. And this is how Aristotle would have thought about this basketball. Now, what two really important thinkers did, I mean, there were others involved as well, but these are the main two. We're going to talk about Galileo and Newton. What they suggested was that actually this picture was wrong. So let's draw our basketballer again. I'm going to draw this with students and get them to draw. We'll draw a basketball hoop like this. And I'll draw the basketball somewhere in midair. And again, draw that kind of trajectory. The basketball hoop like that. Now, what they suggested was that this Aristotelian idea that there must be a force in the direction of motion actually was wrong. And what I want to do in this lesson is really challenge students' idea. They will almost certainly have been taught at primary school that forces are pushes and pulls. The reason we talk about forces as pushes and pulls is because that's really intuitive. We think about what we do with our bodies, we push things and we pull things. So what Aristotle's theory was doing was effectively taking a very human idea and sort of expanding that out to the whole of the natural world. And Galileo and Newton, again, this is why their thinking was so powerful. They were willing to let go of these very intuitive ideas that there must be something pushing it. How else is something going to keep going unless something's pushing it? And say, actually, there's nothing pushing that basketball in the direction of motion. All that's happening here is that there's one force acting, which is this force of gravity. I'm not going to label that for now because we're going to come back to this later in the scheme. Now this is really, really counterintuitive. This is really hard for students to understand. And the reason Galileo in particular thought this picture was nonsense is he was like, well, what's pushing it? And this is something you can question students on. You can say, okay, so if that ball is flying through the air, so what's applying that force? What's giving it that push in the direction of motion? And they won't be able to tell you. And actually the ancient Greek theory, people came up with all sorts of explanations. And actually this was later than the Greeks, but people said, well, maybe the ball displaces air and then that kind of rushes round in a kind of vortex and kind of comes to the back of the ball and keeps pushing it in the direction of motion. When you actually say it, it sounds crazy, but scientists could think of no other way to explain it. And this is because they had this intuitive idea that any object that's moving, let's say at a constant speed, and I'm going to draw that. We'll do all the formalism in later lessons, but I'm going to sort of introduce it now. Let's say this is moving at a constant speed, 10 meters per second or whatever. The ancient idea is that to keep moving at a constant speed, you need something to keep pushing. So I'm going to draw a force like this. Whoops, that should have gone from the center of here. A force like this, there must be a force to keep pushing. That's Aristotle's picture. And the real insight of Galileo and Newton is that they imagined the existence of a world where you didn't have air, you didn't have air resistance. And actually this picture only works if you completely ignore the air resistance. But they said, well, actually, okay, air resistance might cause this to happen in everyday things, but let's imagine stuff where air resistance doesn't act. In that case, if you had an object that was moving at 10 meters per second, let's draw our arrow here like this. The big idea that we want to get across throughout this whole scheme of work is that you don't need a force to keep you moving. If there's no forces acting, I'm just going to move this down. No force acts. The motion doesn't change. Now, this is Newton's first law. We don't even need to call it Newton's first law, although I don't see why you can't. But we're not going to kind of quiz them and say what is Newton's first law necessarily, because what we want them to do, our students, throughout this scheme of work, is use this idea with reference to real life examples. But we're setting it up in this first lesson so that we can keep building it throughout the scheme. If no force acts, then the motion doesn't change. And then the idea that how they took this further was that, okay, let's imagine you've got your object now and a force acts upon it. Let's say there's a force acts this way. This. If a force acts on a moving object, then it can change the motion. So in this case, if it was acting backwards, well, it might mean that object starts to slow down and goes at only 8 meters per second. Or there might be a force this way, like this, and then the object, instead of going that way, would start to go like that, and it would change the direction. And again, it's something that comes up in GCSE specs, this idea that an object can change, a force can change an object's speed, direction, or motion. You don't need to get students to memorize that necessarily. At this point, all we need to do is give them this very, very general idea, which they'll use again and again throughout the scheme, that if a force acts, we get a change in motion. And you could put here change in speed or direction or shape, but I'm just going to put change in motion. And this is the big idea that ties together everything they're going to learn about in this scheme. Now, you might want to give one more example here before you test out whether they're thinking in Aristotelian or Galilean Newtonian terms. And that's the example of the Sun and the Earth. So in the if you were to have the Aristotelian picture, well, the Earth would constantly need a force in the direction of motion to keep pushing it around in orbit. But actually what we know now is, and this is thanks to Newton, who realized that the object of the motion of a basketball is exactly the same. planets out in space, that actually what's happening here is it's exactly the same thing. The only force acting here is gravity. And this was what was so profound about Newton's idea. And you can talk about the apple here if you like. What was special about what Newton realized was that actually the force that was governing the motion of an apple falling from a tree or a basketball flying through the air is exactly the same force that governs the motion of planets or stars traveling in the night sky. And linking these two seemingly unconnected ideas or kind of phenomena and saying actually it's all explicable in terms of the same three laws, that was what made Newton's achievement so extraordinary, that he could literally explain everything from a very small scale to a very large scale with really three very simple, not even bits of maths, just three simple statements about how force and motion are related. And it's really understanding the power of Newton's achievement that this whole scheme of work aims to give to our students. Okay, we'll start to look at forces in more detail next time in a lesson on contact and non-contact forces.